A full-grown Brachiosaurus weighed 80 tons. A Patagotitan reached 100. To exist at that scale, every minute of every day was an engineering problem that would kill anything alive today. Eating 1,000 pounds of plants daily without jaws designed to chew. Digesting it all in a 4-chambered fermentation gut that took over a week to process a single leaf. Walking at precisely 6 kilometers an hour because one wrong step meant shattering bones under their own impossible weight. And cooling a body the size of a building in 35-degree Jurassic heat using a neck that doubled as a biological radiator. They solved problems no animal has ever faced, and the truth of how they did it is far stranger than anything you learned in school. The Jurassic period, 150 million years ago. A world of giant ferns, endless floodplains, and the largest animals ever to walk the earth. But here's the thing, being that big wasn't a superpower. It was a full-time job that started the moment they hatched and never, ever stopped. If you were a sauropod, your entire existence was a balancing act between physics and biology that no creature alive has ever had to navigate. Your bones had to be hollow to save weight, but strong enough to hold up a body heavier than a fully loaded jet. Your lungs had to pull oxygen from an atmosphere that modern scientists still argue about, while a heart the size of a refrigerator pumped blood up a neck stretching over 30 feet into the sky. And that neck? It wasn't just for eating. It was your radiator, your warning system, and your biggest vulnerability, all in one. For decades, sauropods got treated like oversized cows in dinosaur documentaries. Background scenery, something for a predator to chase. But the truth is messier and infinitely more fascinating, because the real drama of their lives wasn't about being eaten, it was about surviving their own bodies. They woke up each morning facing the same questions that would kill a modern elephant in under a day. How do you eat enough while using as little energy as possible? How do you drink without boiling your blood from the effort? How do you sleep when lying down could crush your own lungs? And that's exactly what we're going to unpack. Not the bones in museum halls, but the living, breathing animal, hour by hour, from first light to the fragile silence of night. Because once you see what a sauropod had to do just to exist, you'll never look at a boring dinosaur the same way again. Dawn breaks over the Morrison Formation, 150 million years ago. The air is thick and warm, heavy with humidity and the sweet rot of fallen cycads. Across the floodplain, a herd of giants moves through the mist like slow ships at sea. Brachiosaurus. Each one taller than a 4-story building, each one heavier than 12 African elephants combined. The ground trembles with every step they take. But if you look carefully down near the trampled ferns, you'll spot something that doesn't belong. A hatchling. It's barely the size of a small dog, scrambling between the pillar-like legs of its 30-foot-tall mother. And that contrast, that impossible gap between the tiny newborn and the mountain it has to become, is the key to understanding everything about sauropod life. Because here is the first brutal truth most documentaries skip. An adult Brachiosaurus weighed 80 tons. A Patagotitan could top 100. But every single one of them started life weighing less than 11 pounds. That's right, not 11 tons. 11 pounds, the size of a house cat. And the moment that hatchling tumbled out of its melon-sized egg, a clock started ticking. It had to grow fast, ridiculously fast. Scientists have calculated that during their teenage years, some sauropods packed on up to 2 tons per year. That's not a typo, 2 tons. Every single year, your own body changes by maybe a few pounds annually once you are grown. These animals added the equivalent of a small car in mass, month after month, season after season, for decades. But why? Why the rush? because the world they were born into was designed to kill them. The same floodplain that fed the adults was crawling with predators. Allosaurus, Torvosaurus, animals with serrated teeth and a taste for the young and unprotected. If you were a little sauropod, you had exactly one defense: get big enough that nothing could swallow you. And that race, from bite-sized to almost unkillable, shaped everything about how these animals lived, ate, and died. It's the reason their bones were hollow yet strong. It's the reason their guts were fermentation factories. And it's the reason they walked a tightrope between physics and starvation every single day. Now, let's step back and really look at the world these animals inhabited. The Jurassic wasn't just a backdrop. It was an active participant in their daily struggle. Temperatures were higher than today by perhaps 5 to 10 degrees Celsius. Carbon dioxide levels were 4 to 5 times what we breathe now. And the plants? They weren't the soft, sugary grasses we know. Grasses hadn't evolved yet. Instead, sauropods faced a landscape of gymnosperms, conifers, ginkgos, cycads, and tree ferns, leaves that were tough, fibrous, and coated in thick cuticles to prevent water loss. This vegetation was not designed to be eaten. It was designed to survive. And that meant a sauropod's first problem wasn't just finding enough plants to fill a stomach. The size of a car. It was extracting any usable nutrition from them at all. Think about your own digestive system for a moment. You chew your food. You break it down into a soft paste before it ever hits your stomach, where acids and enzymes take over. A sauropod couldn't afford that. Chewing takes time. Chewing requires heavy jaw muscles and teeth designed for grinding. Sauropods had none of that. Their skulls were remarkably small compared to their bodies. Absurdly small, really. And their teeth? They were simple, spoon-shaped or peg-like, perfect for raking leaves off branches, but utterly useless for chewing. So they didn't chew. They cropped and swallowed. Massive mouthfuls of vegetation whole, ripped and gulped down a throat that could stretch to accommodate food items the size of a human child. And that brings us to the gut, the great mystery chamber, because once those tough, unchewed leaves entered the stomach, they began a journey that would take, by some estimates, between 8 and 16 days to complete. Picture that. You eat breakfast today, and it doesn't leave your body for over a week. In that time, the food sat in a vast, multi-chambered digestive system, a sort of biological brewery, where microbes and bacteria slowly, painfully, slowly fermented the plant matter into something the animal could actually use. This is hindgut fermentation, similar to what you see in modern elephants or horses, but scaled up to a degree that almost defies imagination. The gut of a full-grown Brachiosaurus could hold several tons of fermenting vegetation at any given moment. And that fermentation, it wasn't quiet or cool. It was a chemical furnace that threw off heat, a lot of heat, the kind of heat that, if not managed, would cook the animal from the inside out. And that's where we hit one of the most elegant and terrifying adaptations in the history of life: the neck. That iconic, impossibly long neck. You've seen it in every dinosaur book since childhood, arching up like a living crane. But here is what nobody tells you. That neck wasn't just for reaching high leaves. It was a radiator. Scientists have built models showing that as sauropods grew larger, the surface area of their necks increased dramatically, while the volume of their heat-generating guts increased even faster. But the neck, with its massive skin surface and a network of air sacs running through the vertebrae from the lungs, could dump excess heat directly into the Jurassic air. By pumping warm blood into the neck and letting the breeze do its work, a sauropod could prevent fatal overheating, and the evidence for this is written into the bones themselves. Sauropod vertebrae weren't solid. They were honeycombed with air pockets, part of a respiratory system that was more bird-like than reptile. Air sacs that not only lightened the skeleton, but also cooled the blood supply to the Brain. It was an engineering solution so advanced that human engineers are still trying to fully understand it. But here is the catch. A radiator only works if you can afford to expose it. And exposing a 50-foot neck in a world full of predators is an invitation. One bite to the throat from an Allosaurus, and your blood pressure drops to 0 in seconds. So the very thing that kept you cool also made you spectacularly vulnerable. This tension between cooling and vulnerability, between feeding and mobility, ran through every hour of a sauropod's existence. Now, let's talk about that blood pressure. Because if the neck was a radiator, it was also a plumbing nightmare. To pump blood up 30 feet of vertical neck to a brain the size of a walnut, a Brachiosaurus heart had to generate pressure more than double what a giraffe produces. Estimates suggest a heart weighing up to 400 kilograms. That's nearly 900 pounds of cardiac muscle pounding away in a chest cavity big enough to parallel park a small car. The arteries were thick-walled, elastic, and probably equipped with one-way valves to prevent backflow when the neck moved. And every time the animal lowered its head to drink, that entire system had to adjust instantly, shunting blood away from the brain to prevent a stroke, then reversing the flow when the head came back up. Fail that adjustment just once, and the animal would black out. At 80 tons, a blackout could be instantly fatal. You'd collapse under your own weight, ribs cracking, lungs crushed. So every sip of water was a calculated risk, every bend of the neck, a negotiation with gravity. But perhaps the most relentless pressure was the one that never stopped. Hunger. An adult sauropod needed roughly 1,000 pounds of vegetation per day. That's not an exaggeration. To sustain that enormous fermentation vat, to fuel that titanic heart, to keep those pillar-like legs moving, required a constant input of plant matter. The math is unforgiving. If an average tree fern provided maybe 20 or 30 pounds of edible foliage, you'd need to strip 30 to 50 ferns every single day. And because you couldn't chew, you had to swallow enough bulk that your gut never stopped working. So you walked, slowly, steadily, from tree to tree, your long neck sweeping in arcs across the canopy like a living combine harvester. And walking itself was its own engineering puzzle. Sauropods moved with a straight-legged, columnar gait, their limbs held directly under their bodies like an elephant's. This distributed weight efficiently down through the bones, but it left almost no shock absorption. At 6 kilometers an hour, barely a human brisk walk, the impact forces were manageable. Go faster, and the math turns ugly. Bones would microfracture. Joints would grind. Tendons would snap. The largest sauropods probably never exceeded 10 kilometers an hour, even in a panic, and that burst would come with a high risk of permanent injury. Most of the time, they existed in a state of deliberate, ponderous motion, a life of slow steps and constant grazing, covering miles a day, not for migration, but simply because the food ran out before the hunger did. Yet, for all their solitude of scale, sauropods were not solitary creatures. A remarkable fossil site in Patagonia, dated to 193 million years ago, revealed over 100 eggs and 80 individuals of a species called Mesaurus, ranging from embryos to fully grown adults. The skeletons were clustered by age, hatchlings together, juveniles together, subadults together, the adults in their own group. This is the earliest known evidence of age-segregated herd behavior in any dinosaur. It means these animals lived in complex, socially structured groups. The babies stayed close to each other for protection, perhaps under the casual watch of a few adults while the rest fed. As they grew, they moved through the herd like a graduating class, learning the routes, the water sources, the best feeding grounds. This wasn't a mindless mob. It was a community with shared knowledge passed through generations. And the adults? They communicated in ways we're only beginning to understand. Their calls would have been below the range of human hearing, infrasound, like elephants use today, rumbling through the ground for miles. A distress signal from a juvenile could vibrate through the earth and reach ears too far away to see. A mating call could summon contenders from the next valley. The herd felt each other's presence through the soles of their feet. It was a language of pressure and vibration, silent to our ears but deafening underground. But even in a herd, even with all these adaptations, the day had to end. As the sun dipped below the horizon and the long shadows of conifers stretched across the floodplain, the greatest unsolved problem of sauropod existence returned: sleep. Every large land animal on Earth today must lie down for at least some part of deep sleep. Elephants do it. Rhinos do it. Horses can lock their legs and doze standing, but they still need REM sleep, which requires lying down. An 80-ton Brachiosaurus could not collapse onto a patch of ferns and expect to stand back up in the morning. The sheer mechanics of lifting that much mass from a horizontal position were borderline impossible. Hip joints, muscles, leverage, all of it works against an animal that size. So how did they do it? Did they sleep standing like horses or ostriches? And if so, how did they survive without the deep restorative sleep that lying down provides? Did they take turns? 2 members of the herd always awake, standing guard while the rest somehow, impossibly, rested on their feet. And if so, what happened when a calf, still small enough to be carried off, dozed off in the tall ferns? These are not trivial questions. They cut to the very core of what it meant to be a sauropod. And the answers, when they finally started to emerge from the fossil record, revealed a daily routine more brutal, more fragile, and more extraordinary than anyone had imagined, because the night held dangers that made the daylight predators look merciful. And the way these animals confronted those dangers would rewrite everything we thought we knew about the giants. It is night now. Darkness has swallowed the herd. The temperature drops, the wind shifts. Somewhere in the shadows, something moves. The ground vibrates with a low, subsonic hum, a warning signal from the sentinel. And the question that now demands an answer, the question that will take us deep into the strangest hours of sauropod life, is simply this: what happens when a 100-ton animal tries to fall asleep? The truth starts in a place you'd never expect, with the herald's own throat. The sentinel Brachiosaurus stands motionless at the edge of the herd, a living statue against the stars. Her eyes, positioned on the sides of a head small enough to look almost comical atop that 30-foot neck, scan the darkness in independent arcs. Left eye watching the tree line, right eye tracking movement near the river. This is the first shift of the night watch, and it will last until the moon crosses its zenith. Then another adult will take over, then another. The rotation is relentless, and it has to be. Because here is the thing about sleeping while weighing 80 tons. You cannot lie down. Not fully. Not the way an elephant does, settling onto bent knees with a seismic groan. If a full-grown Brachiosaurus tried that, the pressure on its ribcage would be catastrophic. The lungs, already working against the weight of a body cavity, the size of a delivery truck, would compress to the point of suffocation. The hip joints, built for vertical load-bearing, would dislocate under lateral stress. And getting back up, that's the real nightmare. An elephant can rise from the ground because its legs are relatively short and its center of gravity is manageable. A sauropod's center of gravity sat somewhere in its lower abdomen, behind those massive hind legs. To stand from lying down, it would need to lever its entire front half upward using neck muscles alone, a physical impossibility. At that scale, the math simply doesn't work. So they slept standing, like horses, like ostriches. But horses and ostriches can lock their leg joints and doze without falling over because they, weigh a fraction of a ton, and have 4 legs spaced close enough to catch a stumble? A sauropod had 4 legs? Yes, but they were columns set wide apart, and the animal's sheer height meant any wobble at the hip translated to a swing of several feet at the head. One moment of deep sleep, one loosening of the tendons that kept those pillar legs locked, and the whole animal could topple sideways. At 80 tons, a sideways fall into another herd member could trigger a domino effect that injured or killed dozens. So the sentinel wasn't just watching for predators, she was watching her own herd mates, making sure nobody swayed too far, making sure the juvenile in the middle hadn't wandered, making sure the old male at the rear, the one with the arthritic knee, was still upright and breathing. And this brings us to one of the strangest and most haunting discoveries about sauropods' sleep. Recent research on ostriches, the closest living analog we have for a long-necked, bipedal-capable animal, has revealed something unexpected. Ostriches can enter REM sleep while standing with their eyes open. The brain waves show deep sleep patterns while the bird appears fully awake. This is likely an ancient survival mechanism, and sauropods probably shared it. Imagine that. You are a sentinel on the night watch, staring at a herd of giants in the dark. They seem alert. Their eyes are open. Their heads are up. But inside their skulls, their brains are cycling through dream states. They are asleep on their feet, and you would never know it. The implications are staggering. It means a sauropod herd at night was a collection of animals existing in a fractured state of consciousness. Half the adults in slow-wave sleep, eyes glazed but open. A few in REM, dreaming whatever 80-ton herbivores dream. The sentinel fully awake, scanning, feeling the ground for vibrations. And the juveniles, still small enough to be vulnerable, still growing fast enough to need more sleep than adults, curled in the center of the formation, actually lying down. Because a juvenile under, say, 5 tons could still get up from the ground, could still afford the risk. So the smallest members of the herd got the deepest sleep, guarded by a ring of semi-conscious titans who might be dead on their feet in more ways than one. But the night wasn't just about sleep, it was also about digestion. Remember that fermentation vat we talked about? The one holding several tons of slowly rotting vegetation. That process didn't pause for sunset. If anything, it intensified. The gut microbiome of a sauropod was its most valuable possession, a carefully balanced ecosystem of bacteria and archaea that could break down cellulose and release volatile fatty acids. This microbial army produced methane, enormous quantities of methane. We know from modern cattle that a single cow can produce up to 500 liters of methane per dating. Scale that up to an 80-ton sauropod with a gut capacity thousands of times larger, and the numbers become almost geological. Some researchers have suggested that sauropod herds may have been significant contributors to Jurassic greenhouse gas levels, their collective flatulence warming the very climate they lived in. It's a strange, circular poetry. The heat they generated through digestion warmed their bodies from within and may have warmed their world from without. But methane wasn't the only byproduct. Fermentation also produces heat, lots of it. On a cool Jurassic night, that internal furnace might have been the difference between life and death. The great gut, churning away in the darkness, kept the core body temperature stable even as the air temperature dropped. The neck radiator we described earlier? At night, it could be dialed back. Blood vessels constricted, heat conserved. The animal essentially became a self-heating biological machine, its own digestion serving as a built-in furnace. The cost of staying warm wasn't shivering or seeking shelter. It was simply eating enough the day before. And if you hadn't eaten enough, if the herd had been forced to move too fast, or a feeding ground had been stripped bare, Then, the night became a slow, deadly countdown. Calories burned to stay warm. The gut emptied. By dawn, you'd be weaker, and in a world where weakness attracted predators, that was a death sentence. Now, let's talk about those predators. Because the Jurassic night belonged to the hunters. Allosaurus, the wolf of the Morrison Formation, was built for ambush. 3 tons of muscle armed with a mouthful of serrated teeth. It hunted in packs, probably, and it was smart enough to target the edges of the herd. The very young, the very old, the injured, a limping juvenile who'd cracked a bone trying to keep up during the day's march, an elderly adult whose teeth were worn to nubs and whose gut was slowly failing from malnutrition. These were the ones the Sentinel was really watching for. Not because she could save them, but because their death could trigger chaos. A kill at the edge of the herd could spook the rest, and a stampede of 80-ton animals in the dark was a catastrophe waiting to happen. Broken legs, crushed bodies, calves separated from mothers and left to wander until morning. But here is what the fossil record tells us, and it's not what you'd expect. Sauropod bones from the Morrison Formation sometimes show bite marks from Allosaurus. That's not surprising. What's surprising is that many of those bite marks show signs of healing. These animals survived attacks. They walked away from encounters with 3-ton predators and kept going. This tells us something crucial. An adult sauropod was not defenseless. Its sheer size made it almost impossible for a single Allosaurus to kill. Its tail, long, muscular, and in some species tipped with a whip-like extension, could deliver blows hard enough to shatter bone. Diplodocus, a slightly smaller sauropod contemporary with Brachiosaurus, had a tail that could crack like a bullwhip, potentially at supersonic speeds, creating a shockwave that would deter any attacker. Brachiosaurus had a shorter tail but longer front legs, giving it a powerful forward kick. And the neck itself, that vulnerable-looking radiator, could swing like a 15-meter club. Get hit by that, and you'd be knocked senseless before you ever reached the throat. So predators didn't target healthy adults. They targeted the margins. And the herd's response, shaped by millions of years of evolution, was to close ranks. The Sentinel's warning call, that subsonic rumble we described, would ripple through the ground. Adults would shift position. Juveniles would be herded toward the center. The formation tightened until the herd became a living fortress of flesh and bone, a wall of legs and bodies too dense for any predator to penetrate. It worked. Most nights, it worked. But on the nights it didn't, the consequences were written into the bones of the fallen. This brings us to one of the most intimate and brutal aspects of sauropod daily life: injury. Constant, low-grade, unavoidable injury. Living at 80 tons is not a clean existence. The body breaks down under its own weight in ways that are both predictable and horrifying. Every step a sauropod took sent a shockwave up through its legs and into its spine. Those forces, repeated millions of times over a lifespan of 30 to 40 years, caused microfractures in the vertebrae. We can see them in the fossils. Tiny cracks radiating through the bone, then healing, then cracking again. The skeleton was in a constant state of low-level repair, like a bridge that's never allowed to close for maintenance. And then there were the joints. Osteoarthritis was rampant. Fossil after fossil shows bony growths around the knees, hips, and shoulders, the body's desperate attempt to stabilize joints that were being slowly crushed by gravity. The oldest individuals, the ones who'd reached their species' theoretical maximum size and then kept living, walked in visible pain, their range of motion reduced, their pace slowed. And here is an uncomfortable truth the fossil record makes clear. The largest sauropods ever found rarely reached their species' supposed maximum. That's because the very adaptations that allowed gigantism also imposed an expiration date. Once you passed a certain threshold, the calcium demands of maintaining a skeleton that massive couldn't be met. Bones became brittle. The hollow air sacs that lightened the vertebrae could become sites of infection. The gut, that great fermentation vat, could develop blockages or imbalances that proved fatal. The largest Patagotitan ever found weighed an estimated 57 tons, but the theoretical maximum for the species may have been closer to 70 or 80. No individual ever reached it, because biology, unlike imagination, has limits. And calcium deficiency was just one of the hidden killers. Sauropods laid eggs. Dozens of them, probably in shallow nests scraped into the warm earth. Those eggs needed calcium to form shells. The mother had to pull that calcium from her own skeleton, her own bloodstream, and deposit it into eggs that she would then abandon. Because sauropods almost certainly didn't provide parental care beyond perhaps guarding the nesting ground from a distance. The evidence from that Patagonian site with 100 eggs and 80 individuals, it shows no sign of direct parental feeding. The hatchlings were on their own from the moment they emerged, their bones already adapted for rapid independent growth. They had to find food, avoid predators, and put on 2 tons a year without any guidance from the adults who, at 80 tons, were too large to even notice a hatchling underfoot without crushing it. Think about that for a second. You are born into a world where your own parents are the size of buildings and could step on you by accident. Your survival depends on staying out of their way while simultaneously staying close enough to benefit from the protection of the herd. It's a paradox, and the solution, as revealed by the Mesaurus fossils, is startlingly sophisticated. The hatchlings formed their own groups, separate from the adults like a creche or nursery herd within the larger herd. They moved together, fed together, and grew together. Only when they reached a certain size threshold did they graduate to the juvenile herd, and then later to the subadult herd, and finally to the adult group proper. This age segregation wasn't just social, it was mechanical. An adult sauropod, feeding on high branches, would strip foliage that a juvenile couldn't reach. But the juvenile could feed on lower vegetation the adult ignored. By separating into age groups, they avoided direct competition for food while still benefiting from the safety of proximity. It was an elegant solution to a problem that, at first glance, seemed unsolvable. But let's return to that molten core of the sauropod body, the gut, because to truly understand what daily life was like for these animals, you have to follow the food. You have to imagine the journey of a single cycad leaf, tough and leathery, as it's torn from its branch by a Brachiosaurus tooth and swallowed into darkness. It drops down the esophagus, a muscular tube that in a large sauropod could be over 50 feet long, and lands in the first chamber of the stomach. Here, it's mixed with gastric acids and kneaded by muscular contractions. But the real work hasn't started. The leaf, still largely intact, passes into the hindgut, the colon, a vast coiled labyrinth where trillions of microbes wait. These bacteria and archaea produce enzymes called cellulases, which can break the chemical bonds that hold plant fibers together. The leaf begins to dissolve, not quickly, over days, over a week, over 2 weeks. The microbes release fatty acids, which are absorbed through the gut wall into the sauropod's bloodstream. This is the fuel that powered the giant, not glucose from sugar, like humans run on. Volatile fatty acids, acetate, propionate, butyrate, the same compounds that give vinegar its bite and aged cheese its funk. There was a cost, of course. The microbiome needed to be maintained. If a sauropod ate something toxic, if it ingested the wrong kind of plant or a fungal infection, the consequences could cascade. Modern ruminants can die from bloat when gas builds up in their stomachs and they can't expel it. A sauropod with a blocked gut would face the same fate, but scaled up almost beyond comprehension. Several tons of fermenting vegetation trapped inside a body that couldn't vomit easily, couldn't roll to shift position, couldn't do much except suffer. We have no direct fossil evidence of bloat in sauropods. The soft tissues never preserve, but we have something almost as revealing: tooth wear patterns. The teeth of older sauropods are worn down to flat stubs, sometimes worn completely through to the jawbone. These animals were eating vegetation that was tough and often gritty, with soil and sand picked up from low browsing. All that grit passed through the gut, abrading the walls, causing inflammation, possibly opening pathways for infection. By the time a sauropod reached its 4th decade of life, its digestive system had processed literally thousands of tons of plant matter. Something was bound to go wrong eventually. And yet, despite all of this, the injuries, the gut issues, the calcium debt, the constant predation pressure on the young, sauropods dominated the Jurassic for tens of millions of years. They radiated into dozens of species across every continent. From the relatively modest Magyarosaurus of Europe, a mere 2 tons, to the titanic Argentinosaurus of South America, possibly exceeding 90 feet in length. They were the most successful large herbivores in Earth's history. And the secret to that success wasn't any single adaptation. It was the entire, integrated system. The hollow bones and air sacs, the fermentation gut and radiator neck, the age-segregated herds and infrasonic communication, the slow, deliberate locomotion that maximized feeding time while minimizing energy expenditure. Every piece worked together, and if any single piece failed, the whole animal collapsed. But the most remarkable thing about sauropods isn't visible in their bones. It's in their growth rings. By slicing through fossilized bones and counting the lines, like tree rings, scientists have reconstructed the growth curves of multiple species, and what those curves show is astonishing. Sauropods grew faster than any land animal before or since. A juvenile Brachiosaurus could increase its body mass by a factor of 100,000 from hatchling to adulthood. To put that in perspective, a human baby increases its mass by a factor of about 20 over its entire lifetime. A blue whale, the largest animal alive today, increases by a factor of perhaps 1,000. A sauropod increased by 100,000. The growth rate, especially during the adolescent growth spurt, was almost vertical on the graph. Up and up, season after season, until finally it leveled off. Not because the animal stopped growing, like mammals. Sauropods likely grew throughout their lives, but because the growth slowed to a crawl after skeletal maturity. The curve flattens, and the animal enters its long, slow final phase, living at the edge of what biology permits, for as long as the body can hold together. But growth requires fuel, and fuel requires feeding, and feeding requires movement. And that, at last, brings us to the daily cycle in its full, relentless glory. Dawn. The herd stirs. The sentinel, who has been standing watch for 6 hours, shifts her weight and feels the ache in her joints. Around her, the other adults are already cropping at the nearest trees, their necks swinging in those slow, deliberate arcs. The juveniles are up and moving, jostling each other, practicing the social behaviors that will structure their entire lives. Somewhere in the herd, an old male is struggling. His knee is bad again, swollen and hot. He'll fall behind today. He knows it. The herd knows it. By nightfall, he may be alone or he may be dead. But there's no pause for grief, no ceremony. The herd must move. The food is running out, and the next feeding ground is miles away. The sun climbs, the temperature rises, the neck radiators go to work, blood vessels dilating, heat pouring off the massive surface area of the throat and upper spine. The animals spread out slightly, giving each other room to cool. The juveniles, smaller and more heat-sensitive, stick to the shade where they can find it. The adults plod forward at that steady 6 kilometers an hour, a pace they can maintain for hours without stopping, feeding as they walk, walking as they feed, each mouthful of leaves disappearing down that long throat into the fermentation darkness below. Midday comes. The heat is at its peak, maybe 35 degrees Celsius. The adults slow further. Some stand in what little shade the tall conifers provide, their enormous bodies acting as umbrellas for the juveniles clustered beneath them. This is when the drinking happens. The herd approaches the river, a broad, slow-moving channel lined with ferns. The approach is cautious. Water means mud. Mud means unstable footing. A slip here could be fatal. The adults wade in up to their knees, lower their great necks, and drink. Each swallow is gallons. The total intake for a single adult over the course of a day might reach 200 gallons. 200 gallons of water pulled up through that 30-foot neck against gravity powered by a 400-kilogram heart. The effort is immense. The reward is survival, but water also brings danger. Crocodiles, giant ones perfectly capable of grabbing a juvenile by the leg and dragging it under. The adults know this. They position themselves between the deeper water and the drinking juveniles, their massive legs forming a barrier. If a crocodile lunges, it's going to meet several tons of angry sauropod foot. The crocodiles, smart enough to know the odds, usually stay back. Usually, the afternoon stretches on. More walking, more feeding. 1,000 pounds of vegetation per animal, stripped from the canopy and swallowed whole. The gut churns endlessly, the heart pounds tirelessly. And somewhere in the middle of all this, the old male with the bad knee finally stops. He's done. He can't go any further. The herd continues without him. The sentinel from last night glances back once, maybe her small eye registering the shape of him diminishing behind them. Then she turns forward and keeps walking. By nightfall, the Allosaurus will have found him, or the infection in his knee will have spread to his bloodstream, or he'll simply lie down in the ferns, the first time he's lain down in decades, and never get up again. And this is where our understanding of sauropod life takes its sharpest turn, because for all their size, for all their evolutionary brilliance, sauropods were fragile in ways that are only now becoming clear. The very adaptations that made gigantism possible also made death, when it came, swift and unforgiving. The hollow bones that lighten the skeleton could shatter catastrophically under stress. The fermentation gut, if disrupted, could poison the animal from within. The radiator neck, so elegant in daylight, became a liability in the cold of a Jurassic winter, draining heat that the body couldn't spare. But there's one more piece to this puzzle. One more biological system that defined the sauropod experience more than any other. And it's the system we've barely mentioned because it's the hardest to see in the fossil record. The brain. What was it like inside that tiny head, atop that absurd neck? What did a sauropod know? What did it feel? Was it a simple, instinct-driven eating machine, or was there something richer happening behind those small eyes? The answer, when it finally began to emerge from computed tomography scans of fossil skulls, changed the way paleontologists understand these animals entirely, and it leads us directly into the most intimate hours of the sauropod day. The hours we've been circling and avoiding, the hours when the giants were most vulnerable, most alien, and most tragically recognizable. Because to understand how a sauropod ended its day is to understand something essential about the cost of being huge. And the cost, it turns out, was higher than anyone ever imagined. The brain of a brachiosaurus, when you finally see it reconstructed from CT scans of the fossil skull, is a profoundly humbling object. It is not large. In an animal weighing 80 tons, the brain mass was roughly the size of a fist, maybe a little more. For decades, this was used as the punchline of every dinosaur joke. They were stupid, slow, barely more than walking stomachs. But that joke misses something crucial. The brain wasn't just small, it was specialized. The olfactory bulbs, the part that processes smell, were enormous. The regions associated with social behavior and spatial mapping were well developed. These were animals that lived in a world of scent and sound and vibration, a sensory universe we can barely imagine. They weren't philosophers, but they knew exactly where every member of their herd was, what every tremor in the ground meant, and which patch of forest smelled right. Their intelligence was not an abstract thought. It was in survival, and survival, for an 80-ton animal, was its own kind of genius. But intelligence didn't make them invulnerable. If anything, it made the suffering worse. Because they could feel, they had nerves, pain receptors, the same spinal structures that carry suffering in mammals. When a sauropod fractured a vertebra, it hurt. When its joints swelled with arthritis, it ached with every step. And the evidence suggests they lived with that pain for years, possibly decades. A healed fracture in a fossil tells a story of survival, but it also tells a story of weeks, maybe months, of agony while the bone knitted. And during that time, the animal had to keep moving, keep eating, keep up with the herd, or die. There was no rest. There was no recovery. There was only the endless, grinding demand of the gut and the legs. And that's where we find one of the darkest chapters in the sauropod story. The injuries that never healed. The ones you don't see in museums because the bones are too shattered. The joints too deformed. Paleontologists have excavated sauropod skeletons with evidence of massive infections. Osteomyelitis, a bacterial infection of the bone that turned the hard femur into a spongy, pus-filled ruin. It would have smelled. It would have wept fluid. And the animal would have walked on it anyway, because not walking meant not eating, and not eating meant a faster death. The herd wouldn't stop for a single wounded member. It couldn't. The herd's survival depended on the collective feeding, the constant forward motion. So, the wounded one limped along, day after day, its immune system fighting a losing battle against bacteria that entered through a cracked bone from a fall or a bite wound that never closed. And falls were more common than you'd think. We imagine sauropods as utterly stable, their four-pillar legs planted firm. But fossil track sites reveal moments of chaos, footprints that suddenly stagger, drag marks in the mud where a leg gave out, imprints of a body that hit the ground and struggled to rise. Some of these trackways end at the body mark. The animal fell and never got up. The cause could be anything. A misstep on a slick riverbank, a collapse from sheer exhaustion, a seismic event that shook the ground. But the result was the same. A mass of flesh and bone, 80 tons of it lying on its side, the great lungs crushed under the weight of its own ribs, the heart straining against gravity in a direction it was never designed to beat. Death by falling is one of the most terrifying ways to go when you are that big, and the fossil record suggests it happened more often than any predator attack. Now, let's shift to something that sounds almost mundane, but was equally lethal. Parasites. The sauropod gut was a rich, warm, dark environment, perfect not just for beneficial microbes, but for worms, nematodes, flukes, tapeworms. Coprolites, fossilized dung, from sauropods have been found containing parasite eggs, some species still recognizable today. Imagine the discomfort. Several tons of fermenting plant matter, already churning and gaseous, now also home to a writhing ecosystem of intestinal parasites that could grow to lengths measured in meters. The animal couldn't reach its own belly to scratch, couldn't dislodge the worms with anything except the slow grinding of the digestive tract itself. In some individuals, the parasite load may have been so heavy that it leached away the calories the food provided, turning the 1,000-pound daily intake into nothing more than enough to feed the worms. Malnutrition, even while eating constantly, a slow starvation hidden inside a giant. But nutrition was also about chemistry, and that brings us to the plants. The Jurassic flora didn't want to be eaten. Cycads, a staple of the sauropod diet, manufacture a variety of toxins, sakaisin, a potent neurotoxin, and other compounds that can cause liver failure in modern animals. Conifers produced resins and terpenes, volatile chemicals that irritate the stomach and disrupt digestion. To eat these plants day after day, sauropods needed a liver of incredible power, a biochemical detoxification system that could neutralize poisons before they entered the bloodstream. And we know they had it because they survived. But the cost of that detoxification was borne by the liver cells, which over a lifetime accumulated damage, fatty deposits, scarring, possibly cancer. We have no sauropod liver fossils, but we can infer from the plants they ate and the teeth that ground them that every meal was a calculated chemical risk. The wrong patch of cycads, too young and too rich in toxin, and the body couldn't keep up. But the moment that truly redefines what it meant to be a sauropod, the moment it gets worse in ways you didn't expect, is when we look at the bones of the very young and the very old together. At the Mosasaurus site in Patagonia, the fossilized hatchlings are not scattered at random. They're clustered in groups, and some of those groups show signs of a single catastrophic event: a flood, a flash fire, a collapse of the nesting ground that buried dozens, maybe hundreds of eggs and hatchlings in a single afternoon. The tiny skeletons are preserved in the same layer, their ribs intact, their little necks curled in positions that suggest they died struggling. This was not predation. This was chance. A storm, a river overflowing, and an entire generation of sauropods was wiped out before they could grow beyond the size of a small dog. The adults, miles away and too large to even notice the loss, simply continued their march. The herd went on, but the future had been erased. This is the great vulnerability of the R-selected reproductive strategy. Sauropods laid dozens of eggs per clutch, probably multiple clutches, per season, and then walked away. No parental care, no feeding of the young. Statistically, this works because you produce so many offspring that a few will survive. But it also means that the emotional bond between adult and calf was non-existent. There was no mourning, no grief, just the cold math of survival. And yet, we see in those age-segregated herds something that looks almost like a society. The juveniles associating together, the subadults in their own gangs, the adults tolerating them but not actively protecting them. It's a system that worked for millions of years, but it was utterly ruthless. For every one sauropod that reached 80 tons and 40 years old, thousands of siblings died as eggs, as hatchlings, as juveniles caught by predators before they could grow their defenses. The life of a sauropod was a lottery with terrible odds, and only the extremely lucky got to experience the slow, grinding pain of old age. And the old age itself was a betrayal. Remember the calcium deficiency we mentioned. As a sauropod aged, the demands of maintaining a skeleton that weighed several tons outpaced the ability to extract calcium from food. The bones became brittle. The hollow air sacs in the vertebrae, which in youth had been a brilliant weight-saving trick, now became a liability. The thin bone walls could crumble under the stress of simply holding the neck up. We see evidence of collapsed vertebrae in some specimens, the bone literally compressed and fractured in a way that would have pinched nerves and caused chronic, unrelenting pain. An old sauropod might have lived with a partially paralyzed neck, unable to lift its head as high as it once could, forced to browse lower and lower, competing with smaller herbivores for food it needed to survive. The great high browser, the ultimate canopy feeder, reduced to eating ground-level ferns, its elegant neck now a burden, the radiator still trying to cool a body that was slowly failing. And then there's the mystery that haunts every paleontologist who studies these giants. Why do we never find the truly old? The theoretical maximum size for a Brachiosaurus or a Patagotitan is not seen in any fossil. The largest individuals are always a bit smaller than the models predict they could be. It suggests that something always stops them. Predation? Not for adults. Starvation? Possible. But they could switch to lower quality food. The real answer might be something more subtle and more horrifying. The gut itself became the enemy. As the animal aged, the microbiome shifted. The fermentation vat lost efficiency. Gas production increased. Methane levels rose to the point where the animal could no longer expel it. Bloat, the silent killer of cattle, scaled up to dinosaur proportions. Imagine the pressure. The internal organs pressed against the diaphragm. The lungs compressed. Breathing became shallow, then impossible. The great heart, still beating, pushed against a wall of gas that had nowhere to go. Death by indigestion. The most mundane end imaginable for the biggest animal that ever lived. But let's not end on that, because the story of sauropod daily life isn't just a catalog of suffering. It's also a story of breathtaking adaptation. In the middle of all this fragility, there were moments of something like triumph. The way they used sound, the infrasound that traveled through the ground, wasn't just a warning call. It was a constant hum of presence. Each herd member could feel the footsteps and the heartbeats of the others, even at great distance. In the darkness of the night, when no eyes could see, the ground itself was a telegraph. The sentinel could feel a juvenile's distress. The mother could feel the approach of a stranger. It was a form of connection we cannot replicate, a community held together by pressure waves and seismic whispers. And it suggests something beautiful, that in those vast, slow, seemingly solitary lives, there was a kind of intimacy. The herd moved together not just out of instinct, but out of a physiological synchronization. Breathing rates aligned. Heartbeats matched. The great bodies, each a universe of fermentation and bone, pulsed in a communal rhythm. You might call it a form of distributed life. Not an individual, but a herd as a superorganism. Each member a cell in a larger body that stretched across the floodplain. When one died, the others felt the absence in the quieting of the ground. Not grief, perhaps, but a shift in the pattern, a missing note in the bass line. And that brings us, at last, to the moment the day ends and the night begins again. The sun sets for the 1,000th time in the life of an old female Brachiosaurus. Her knee has been bothering her for years, but today it's worse. She has eaten her 1,000 pounds, drank her 200 gallons, walked her 10 miles at 6 kilometers an hour. She is exhausted. Around her, the herd is settling into the night formation. The sentinel takes her place. The ground begins to hum with the infrasonic calls that mean safety. The old female stands with her eyes open, and she lets her mind slip into that strange standing sleep, the REM that comes without the fall of eyelids. She dreams. We don't know what she dreams. Maybe of the nest she left behind decades ago, the hatchlings she never saw. Maybe of the taste of a particular cycad from her youth. Maybe she dreams nothing at all. But she stands, swaying almost imperceptibly, her massive frame held upright by locked tendons and millions of years of evolution. And for a few hours the greatest engineering problem the animal kingdom ever solved is quiet. The gut churns, the heart beats, the neck cools, and the old female, who has outlived her siblings, 100 to 1, survives the night. But the night is not done with her. And what waits in the pre-dawn darkness, the hours when the world holds its breath and even the sentinel's attention wavers, is a crisis that no amount of evolutionary adaptation can solve. A crisis that will reveal, at last, the true limit of being huge. And it begins not with a roar or a shaking earth, but with something far more intimate, a single microscopic crack. The crack is in her 6th cervical vertebra, a hairline fracture so fine that even a modern CT scanner would struggle to detect it. It runs along the thin wall of bone that separates one of the pneumatic air sacs from the spinal canal. For 37 years, that wall has held, through every swing of her neck, every drink from the river, every glance upward to check for predators, it has flexed and compressed and borne the load, without complaint. But bone, like any material, has a fatigue limit. And tonight, in the cold hour before dawn, when the Jurassic air is at its densest and her body temperature has dropped just enough to make the bones slightly more brittle, the accumulated microfractures of a lifetime finally connect. The crack propagates. It's not loud. There's no snap like a breaking branch. Just a sudden shift inside her, a sensation she doesn't have the neurology to understand, a wrongness that makes her open her eyes fully for the first time in hours. She is still standing. The tendon locks in her legs are still engaged. The sentinel has noticed nothing. The herd around her is a field of slow-breathing shadows, but something has changed irrevocably. The crack has opened a channel between the pneumatic air sac and the tissues surrounding her. Spinal cord, air, under pressure from her respiratory system, begins to leak out. Not much at first. A tiny stream of bubbles infiltrating the paravertebral muscles. But the air sacs in a sauropod's neck are part of a bellows system that powers the lungs. Every breath she takes pushes more air through the network, and now some of it is escaping into places it should never go. The muscles on the right side of her neck begin to swell, just slightly, with what will eventually become subcutaneous emphysema. She doesn't know this. She only knows that her neck feels strange, heavy, a little harder to lift than it was at sunset. Dawn comes. The herd stirs. The sentinel finally relaxes her vigil and begins to feed. The old female tries to follow suit. She swings her head toward a cycad frond, and that's when it happens. The movement, which should have been as natural as breathing, sends a bolt of pain down the right side of her neck. The leaked air has dissected between muscle layers, separating them, putting pressure on nerves. Her head jerks back, she freezes. The other adults don't notice. They're already stripping the canopy, their small heads moving in that slow, serene arc. She's performed 1,000,000 times. For the first time in her life, she cannot do it. She tries again. The pain is worse. The crack, still microscopically small, has destabilized the vertebra. Any significant movement risks widening it. The nerves that control the right side of her neck are firing in panic, telling her brain that the limb is in danger. But a sauropod brain cannot override that signal. It can only obey. She lowers her head to browse at lower branches, hoping to find something she can manage. The pain eases for a few minutes. She manages to strip leaves from a ginkgo sapling, the soft foliage reassuringly familiar. She swallows. The food begins its long journey to the fermentation vat, but the relief is temporary. The crack has set in motion a cascade that will not stop. As she moves even slowly, the bone grinds against itself. Microscopic fragments break off. Some drift into the air sac, where they will eventually be coughed out, if she lives that long. Others enter the bloodstream through the damaged capillary network, triggering an immune response. Her body temperature, already high from the gut's fermentation, ticks upward another fraction of a degree as the inflammatory process begins. She is now fighting an injury she cannot comprehend, using tools her body has but poorly adapted to the task. The herd begins to move. The morning march to the next feeding ground is underway. The old female takes a step. Her knee, the arthritic one, screams at her. That pain she knows. She has known it for years. She limps forward, falling in near the rear of the column. The neck is stiff now, swollen on the right side, a visible lump pushing against the skin that the other members of the herd can probably smell. Infection has not yet set in, but the injury signals are there. In modern animals, a sick or wounded herd member is often subtly excluded. The healthy ones keep a little more distance. They're not cruel. They're just responding to the altered chemistry of the wounded animal's scent. The old female finds herself a few paces further back than usual, then a few more. The herd doesn't pause. It can't. By midday, she is in trouble. The neck swelling has worsened. The crack is no longer hairline. The constant movement has widened it to a millimeter. Bone spurs are already beginning to form as the body tries desperately to stabilize the fracture. But the location is terrible. Every swing of the neck, every step that jostles the spine, disrupts the delicate scaffolding of healing cells. She is losing strength on her right side. The neck droops slightly. Her head, which should be held high to scan for danger and cool her blood, now hangs lower than her shoulders. The radiator is failing. Her core temperature rises. The fermentation vat, already a furnace, begins to overheat. The microbes that break down her food are sensitive to temperature shifts. Too hot, and they die. The fermentation slows. The fatty acids she depends on begin to diminish in her bloodstream. She is eating, but she is starving. And then the real killer arrives. Infection. With the air sac breached, bacteria from the respiratory system, which are always present, even in a healthy sauropod, now have a direct path into the sterile interior of the vertebra and the surrounding muscle. They multiply. The immune system mounts a massive response, flooding the area with fluid and white blood cells that have no good way to exit the bone. The pressure inside the vertebra builds. The pain, already severe, becomes agonizing. She stops trying to feed. She can't. Every movement of her head is a new spike of torment. She stands still on the floodplain, the herd moving away from her, one of the juveniles glancing back briefly before hurrying to catch up. The old female is now alone in the worst sense. She is upright, alive, and utterly isolated. A mountain of flesh slowly being consumed from within by an enemy too small to see. But the body has one more desperate trick. The cracked vertebra, under the influence of inflammatory signals, begins to lay down new bone. Wild, disorganized, hyperactive bone growth, the kind of pathological fusion that paleontologists find in sauropod skeletons and puzzle over. It's an attempt, crude but sometimes effective, to splint the fracture. If she were younger, if the injury were elsewhere, it might work. But she is old, her calcium reserves are depleted. The new bone is weak, porous, and badly anchored. Even as it forms, the stress of holding up her neck causes it to crack again. The body builds, the motion breaks. It's a race she is losing, and the effort consumes the last of her metabolic reserves. She has not eaten significantly in 3 days. The gut is now mostly empty, the fermentation vat running on fumes. The heat production drops sharply. For the first time since she was a hatchling, she feels the cold. Night comes again. The herd is miles away. She cannot hear their infrasonic calls. The ground is silent. She is standing in the same floodplain. Her great body now a monument to engineering failure. The neck, the elegant radiator, is now a swollen, infected, useless appendage. The legs are locked, but her weight is shifting. She sways. The right foreleg, which has been compensating for the bad knee, finally gives a tremble. A small slip, nothing dramatic, but enough to twist the spine, to put lateral pressure on the fractured vertebra. The weakened bone gives way. The crack opens fully. Bone shards cut into the spinal cord. She doesn't feel it, not the way we would. In that instant, everything below the neck goes silent. The legs, which have supported her for 37 years, lose their signal. The tendon locks release. She is falling and she doesn't know it. The descent takes perhaps 3 seconds. Her massive body tilts, slowly at first, then with gathering momentum, until her right shoulder hits the ground with a sound like thunder. The impact shatters several ribs. The gut, still holding a few tons of half-fermented plant matter, ruptures internally. The heart, the great 400-kilogram heart, tears free of its moorings. She is unconscious before the pain can register, if there is any pain left to register. The night swallows the sound. The herd does not hear. Dawn reveals her. The corpse of an 80-ton Brachiosaurus is an ecosystem. Even before the sun fully rises, the scavengers have arrived. Small theropods, pterosaurs from the coast, a swarm of insects that have already begun to colonize the fermenting gut. By midday, the Allosaurus will come. They'll tear at the softer tissues, the belly, the throat, leaving the massive limbs and the failed neck. The bones will be scattered by floodwaters eventually, carried downstream to be buried in fine sediment. Millions of years later, a paleontologist will find a single broken vertebra, fused and deformed by infection, and wonder what happened. She will hold it up to the light and see the evidence of the crack, the bone spurs, the desperate attempt to heal. And she will know, with a certainty that only the fossil record can provide, that this animal lived with its injury for days, maybe weeks, that it suffered. And that, in its suffering, it revealed the true cost of being huge. But the story doesn't end with that single broken bone. Because the old female was not unique, the fossil record is full of sauropods with similar pathologies, healed fractures that fused badly, vertebrae collapsed and rebuilt, joints encased in arthritic growth. Every one of these fossils is a chapter in a much larger narrative about what it meant to live at scale. The daily life of a sauropod was not a peaceful stroll through a fern meadow. It was a high-wire act performed without a net. Every step, a negotiation between the demands of physics and the limits of flesh. The adaptations were brilliant. The air sacs, the fermentation gut, the radiator neck, the age-segregated herds. But they were not perfect. They couldn't be. Perfection would require a world without wear and tear, without accidents, without the slow accumulation of damage that time and gravity impose on all living things. And here is the surprising detail that changes how you'll see every sauropod skeleton from now on. Recent analysis of those bone scars has revealed that many of the worst injuries occurred not in the oldest individuals but in the prime adults. The ones in their late teens and early 20s. The ones who, by all appearances, should have been at their physical peak. The reason, paleontologists now suspect, is that this was the period when sauropods were still growing relatively fast while also reaching the size where their weight began to seriously stress their joints. A juvenile at 15 tons can afford to tumble and get up. An adult at 60 tons cannot. But a 20-year-old, still putting on mass, still pushing the limits of what its skeleton can support, occupies a dangerous middle ground. Its bones are denser than a juvenile's, but not yet fully stabilized. Its coordination is not yet fully adapted to its own changing dimensions. It is, in other words, a teenager who doesn't know its own strength, and the consequences are catastrophic. The most frequently injured sauropods were the ones who should have been the future of the herd. And when they fell, they left a gap in the social structure that took generations to fill. This explains something that had long puzzled paleontologists: the peculiar age distribution in sauropod bone beds. You find lots of very young skeletons. You find lots of very old skeletons. But the middle-aged adults are disproportionately rare. It's a mortality curve shaped like a U. High death rates for hatchlings, unsurprising given the predation and environmental hazards. Then a dip in mortality for the juveniles who've grown large enough to be relatively safe. Then a spike again in early adulthood, when the body's growth and the external pressures combine to make injury and death more likely. And finally, for the very few that survive past that spike, a long, slow decline into old age, with its own suite of degenerative problems. The curve tells a story of constant, grinding attrition. For every brachiosaurus that lived to see its fourth decade, dozens died at 22, their bones crushed under their own weight, their potential unfulfilled. But there's another layer to this. The herd. We've described it as a protective formation, a social structure that buffered the young and the vulnerable. But what happened when the herd lost too many of its prime adults? The sentinel shifts, the infant rearing support, the knowledge of migration routes and water sources, all of it depended on a critical mass of experienced individuals. If too many died in that dangerous middle age, the herd's collective memory degraded. Watering holes were forgotten. Feeding grounds went unused. The cohesion that held the herd together during predator attacks weakened. A herd under chronic stress from high attrition would eventually begin to fail, not from a single catastrophic event, but from the slow erosion of its institutional knowledge. The sauropods, for all their size, were only as strong as the social bonds that connected them. And those bonds, like bones, could fracture. This brings us back to the old female. Why did she survive for 37 years when so many of her age cohort died young? The answer is written in her bones, preserved in that same fused vertebra. The pathological bone growth that tried to heal her fracture didn't start with the fatal crack. It started decades earlier. She had suffered a similar injury in her youth, probably a stress fracture from a fall, and she survived it. The bone healed, poorly, but effectively, and she went on to become a mother, a sentinel, a repository of memory for the herd. She knew the safe paths. She knew the deep waterholes that never ran dry. She knew the sound of a pack of Allosaurus planning an ambush and the subsonic call that told the juveniles to freeze. She was, in a very real sense, the herd's living library. And when she fell, all that knowledge vanished. The herd would adapt, as it always did, but something irreplaceable was lost. This is the mundane, breathtaking truth at the heart of sauropod existence. They were not monsters. They were not indestructible. They were animals, caught in the same cyclical struggle that defines all life. The engineering problems were vast, but the solutions were temporary. The giant body was a magnificent machine, but it was a machine that wore out, that broke down, that required constant maintenance and came with no warranty. And in its breaking, it produced the fossil record that we now study, piece by painful piece, to reconstruct what daily life was really like. One such piece was unearthed in 1999 in the Morrison Formation of Wyoming, a trackway of a large sauropod, probably a Diplodocus relative, preserved in a limestone slab. The footprints are uneven. The right forelimb is dragging, leaving a furrow in the ancient mud. The stride length is shorter than normal. Something is clearly wrong with the animal. The trackway continues for tens of meters, then stops abruptly at what can only be described as a body impression. A large, shallow depression where something heavy fell and did not get up. Around it are the footprints of theropods, converging from multiple directions. The story is written in stone. An injured sauropod, abandoned by its herd, limping across a floodplain until it finally collapsed, whereupon the scavengers came. It is a story we can read, almost frame by frame, and it happened not once but many times, across the Jurassic, across the Cretaceous, across the entire 150 million year reign of the sauropods. But there is one more revelation, one more layer of the daily life that we've barely touched because the evidence is so fragile it almost never survives. The skin. In a handful of sites around the world, sauropod skin impressions have been found preserved in the same fine sediment that captured their bones. The skin was not smooth and leathery like an elephant's. It was pebbled with scales, some the size of a fingernail, others the size of a dinner plate. arranged in patterns that likely varied by species and by age. And in one remarkable specimen from Argentina, the skin impression shows something unexpected. An old, healed wound, a tear, maybe from a predator's claw or a tree branch, that had scarred over with a different scale pattern. The scar tissue was tougher, darker, a permanent patch in the great quilt of the animal's hide. It must have itched as it healed. It must have pulled with every movement. And yet the animal carried it for years, a visible record of a single bad day in a life that otherwise went on. That scar is, in miniature, the entire story we've been telling. The sauropod body was a canvas on which its life was recorded, every injury and every recovery, inscribed in bone and skin and tooth wear. The daily life was not a single narrative but an accumulation of moments, most of them lost, a few of them fossilized for us to find. And what those moments tell us, when we piece them together, is that the biggest animals that ever lived were, in their own way, among the most vulnerable. Their size was not a shield against suffering. It was the source of it. The neck that let them reach the heavens was the same neck that broke and killed them. The gut that fermented their food was the same gut that could poison them with its own byproducts. The herd that protected them was the same herd that had to leave them behind. Every advantage had a cost. Every giant was a walking paradox. And so, as the sun sets on our old female, now scattered in pieces across the floodplain, we are left with a question that the fossil record cannot answer, but that we have earned the right to ask. What was it worth? 37 years of constant eating, constant walking, constant pain management, 3 decades of slow movement under an unblinking sun, dodging predators, weathering storms, trying to reproduce, trying to stay upright. A life spent solving problems that no animal has ever solved, only to be undone by a crack too small to see. Was it suffering, or was it simply being? And does the question even make sense to a creature whose brain, however specialized, could never have formulated it? The answer, if there is one, lies not in the bones, but in the continuity. The old female died, but her species survived for tens of millions of years. Brachiosaurus and its kin walked the earth, their daily rhythms unfolding in countless variations on the themes we've explored. They lived, they ate, they slept standing up and dreamed their standing dreams. They communicated in vibrations and felt each other's presence through the soles of their feet. They experienced something, we cannot call it happiness, we cannot call it sorrow, but something that was deeply, inarguably alive, and when they died, they left behind a record that we are only now learning to read. A record etched in calcium and pressure, in fossilized dung and skin impressions, in trackways that lead to body impressions and bones that show the marks of healing. The mundane, breathtaking truth is that sauropods lived lives as complex and fragile as our own, scaled up to a dimension that challenges our understanding of what life can be. And that truth, once seen, cannot be unseen. Every museum mount, every articulated skeleton towering over a gallery, is not a monster from a lost world. It is a biography, a life, written in stone, waiting to be read. We are the first generation in history to read that biography front to back. And what it says about the sauropods, about their bodies, their pain, their slow and strangely communal lives, is only half the story. The other half is what it says about us, because we look at an 80-ton animal and see a monster. We imagine invincibility. We assume that size solves every problem, that the big things have it easy, that the small and fragile are the only ones who truly suffer. But the sauropod teaches the opposite lesson. The bigger you are, the harder you fall. Literally, the more complex the engineering, the more catastrophic the failure. The longer the neck, the farther the crack can travel before anyone notices. This is not just a dinosaur fact. It is a principle that governs everything from skyscrapers to empires to the bodies we inhabit right now. The systems we build to protect ourselves eventually become the sources of our greatest vulnerability. The sauropod's hollow bones lightened its load and also doomed it when the cracks finally connected. The fermentation gut that powered its life could poison it from within. The herd that kept it safe had to leave it behind. Every solution was temporary. Every advantage had a shelf life. And yet, for tens of millions of years, the sauropod strategy worked. Not perfectly, but persistently. Not without suffering, but with a kind of stubborn biological grace. What do we take from that? Maybe it's this. There is no perfect adaptation. There is no life without injury. No growth without fracture. No community without abandonment. The sauropod lived in that tension every minute of every day, and it never resolved it. It just kept walking, 6 kilometers an hour, 1,000 pounds of plants, 200 gallons of water, standing sleep. Infrasonic calls fell through the soles of its feet. A life that was, in its own way, as full of routine and risk and fleeting connection as anything we experience. Different in scale, different in sensory world, but recognizable at the level of simply being. That recognition is the real gift of the fossil record. It turns a museum skeleton from a static monument into a mirror. You look up at that towering neck, and you see an animal that got hungry, got tired, got hurt, and got old. An animal that had a favorite feeding ground and a bad knee and a social circle it depended on. An animal that stood in the dark with its eyes open, dreaming. It is easy to dismiss dinosaurs as too alien to matter, too far removed to teach us anything about ourselves. But the bones disagree. The bones are diaries. And every page says the same thing in the same ancient handwriting. To be alive is to solve problems that have no permanent solution, to carry injuries that will never fully heal, and to keep moving anyway. So the next time you see a sauropod in a documentary, watch closely. Not for the spectacle of its size, but for the small things. The way it shifts its weight from leg to leg. The way it scans the tree line with that tiny head. The way it checks on the juvenile in the ferns. These are not computer-generated animations of a dead thing. They are reconstructions of a life that actually happened in all its mundane, painful, magnificent detail. And the fact that we can reconstruct it at all, that a broken vertebra from a Wyoming hillside can tell us about an animal's final 3 days of suffering, that a trackway in Argentina can show us a limping giant abandoned by its herd, that a coprolite can reveal the parasites that lived in its gut, is nothing short of miraculous. Paleontology is not the study of bones. It is the study of persistence. The persistence of calcium in rock, the persistence of a scar in fossilized skin, and the persistence of questions that we have been asking since the first human being saw a dragon's tooth in a cliff and wondered what could possibly have been that big. We still wonder, and that wondering, that unquenchable curiosity about what daily life was really like for the giants of the Jurassic, is what drove this entire journey. We started with a hook about 80-ton engineering problems. We traced the food through the fermentation vat. We walked with the herd through the heat of midday and the terror of the night. We watched an old female fall, and we realized that the line between triumph and tragedy is thinner than a hairline fracture. Now, standing at the end of that journey, I have one more thing to leave you with. If you found yourself moved by the old female's story, if you felt a pang when the herd left her behind, or a strange comfort when you learned that the juveniles formed their own little creche and survived together, then you have just proven something important. We don't care about these animals because they were monsters. We care about them because they were alive. And once you see the life behind the bones, you can never unsee it. Every sauropod fossil is a biography. Every trackway is a diary entry. Every healed fracture is a story of survival against terrible odds. Keep that in mind the next time you drift off to sleep. You are lying down, fully horizontal, your lungs expanding effortlessly, your joints unloaded, your brain cycling through REM in safety and warmth. The old female Brachiosaurus never got to do that. She stood in the dark, her legs locked, her eyes open, her fractured vertebra slowly splitting under the weight of a neck that had carried her through 37 years of Jurassic life. And she did it so that her species could persist, so that the herd could continue, so that the biography would be written. If that doesn't earn your respect, I don't know what will. Thanks for spending this time in the late Jurassic with me. If you want to explore more of history's strangest daily lives, the routines, the struggles, the mundane truths behind the big stories, then take a second to like this video and subscribe. We do deep dives into the lives that textbooks ignore, and we've got a lot more coming. Drop a comment letting me know where you are listening from and what time it is for you. And if you have a particular historical figure or creature you'd like us to cover next, leave that in the comments too. I read them. Now dim those lights, burrow into your blankets, and sleep well. You've earned it. And unlike a sauropod, you get to do it lying down.